Applications of differentiation. So at the end of this lesson, students should be able to solve optimization problems. Okay, so the steps to solve optimization problems. First, you need to read the problems carefully, sketch a picture or diagram, write down the known facts together with any relationships involving the variables. So meaning you have to take out all the infos. Okay, determine which variable to be maximized or minimized. Find the critical numbers. You need to get the first derivative and equate to 0 to get your values of your x's. Then find the extremum by using the second derivative test. So meaning you need to get your f double prime x. Let's look at the first example of optimization problems. A farmer wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. Find the largest area of the field if only 2,400 meters of fencing is available. So let's say this is your river. So this is your field. This side is x, x, y. So meaning x plus y equal to 2,400. So 2x plus y equal to 2,400. So y equals to 2,400 minus 2x. That's your first equation. So we have area A equal to x times y. So x 2,400 minus 2x. So A equal to 2,400x minus 2x squared. So find your dA dx. So we have 2,400 minus 4x. For largest area, so dA over dx equal to 0. So we have 2,400 minus 4x equal to 0. 4x equal to 2,400. X equal to 600. So get the second order derivative, d squared a over dx squared. So we get negative 4, which is negative value. So that turns out to be maximum area. Hence, when x equal to 600, so A equal to 2400 times 600 minus 2 times 600 squared. So we have 720,000. So hence, the largest area of the field is 720,000 meters squared. Let's look at the second example on optimization problems. A closed right circular cylinder of base radius r cm and height h cm has a volume of 54 pi centimeter cube. Given that the total surface S of the cylinder is given by this formula, find the radius for which the surface area is minimum. First, we need to differentiate. So ds over dr equal to negative 108 pi or negative 2 plus 4 pi r. So for surface area minimum, so we get ds over dr equal to 0. So negative 108 pi over r squared plus 4 pi r equal to 0. Negative 108 pi plus 4 pi r cube equal to 0. So we have 4 pi r cube equal to 108 pi. So r cube equal to 27, r equals to 3. So get second order derivative, d squared s over dr squared. So we have it as 216 pi r negative 3 plus 4 pi. So when r equals to 3, so d squared s over dr squared equals to 216 pi over 3 squared plus 4 pi. So we get it to be 12 pi, which is greater than 0. So hence this is the minimum area. So hence the surface area is minimum when r equals to 3. 10.2 Rate of change. Students should be able to solve problems regarding rate of change, including related rates. Right, what do we mean by rates of change? So rate of change of a quantity refers to how the quantity changes over time. So meaning this is with respect to t. So rate of increase will be positive, rate of decrease will be negative value. Let's look at the first example. The side of a cube is increasing at the rate of 5 cm per second. Find the rate of increase of the volume when the length of a side is 3 cm. So let the side be x cm. So we are given the x dt to be 5 cm per second. So we need to find dv over dt when x equal to 3. So volume of a cube, v, x cube, so dv over dx, 3x squared. So we want to find dv over dt, so that is dv over dx times dx over dt. So substitute 3x squared times 5, so we get 15x squared. So that is our dv dt. When x equals to 3, dv over dt equals to 15, 3 squared, so we get 135 cm cubed per second. Hence, the rate of increase of volume is 135 cm cubed per second. So example 10, a spherical balloon is being inflated with helium at a steady rate of 150 cm cubed per second. So if you look at the unit, that is cm cubed, so that will be the volume. So volume BV, so surface area BA. So you are given dV dt as 150 cm cubed per second. So find the rate at which the surface area is changing. So we need to get dA over dt. So when radius equal to 6. So volume V will be 4 over 3 pi r cubed. So dV over dr, we get 4 pi r squared. So area will be 4 pi r squared, so dA over dr, 8 pi r. So we want dA over dt, so that will be dA over dV times dV over dt. So we need to use what's given. We are given dV over dt. Okay, but we don't have yet the dA over dV. But we can use dV over dr and dA dr. So dA dV, that will be dA over dr times dr over dV times dV over dt. So let's substitute. So dA over dt, that will be dA dr is 8 pi r times dr dV, so that we 1 over 4 pi r squared times dV dt, given just now as 150. So simplify, we get 300 over r. When r equal to 6, so dA over dt, 300 over 6, so we get 50 cm squared per second. So area power of 2. Hence, the rate of change of surface area is 50 cm squared per second. Let's look at example 11. So water is running at a steady rate of 36 pi centimeter cube per second into a right inverted circular cone with a semi-vertical angle of 45 degrees. Find the rate of increase in water depth when the level of the water is 3 cm. So again, you look at the unit here. So that is for volume. So dV over dt, 36 pi cm cube per second. So we have a semi-vertical angle of a right inverted circular cone. So let's try to sketch. So this is your cone. So this is your 45. So let's take out the triangle. So this is 45. Let the height will be h. So this is h. This is your radius. So we have tangent 45. So this is the opposite. So r over h. So tangent 45 is 1. So r over h. So we get h equal to r. So find the rate of increase of water depth. So we need to get dh over dt when h is 3 cm. So volume V equal to 1 over 3 pi r squared h. So substitute r. So we need the dv dh. So V equals to 1 over 3 pi. R is h. So get V equals to 1 over 3 pi h cubed. So we get dv over dh. That will be pi h squared. dh dt, dh over dv times dv over dt. So dh over dv, that will be 1 over pi h squared. So dv dt, substitute as 36 pi. So that is equal to 36 over h squared. When h equal to 3, dh over dt, so 36 over 3 squared. That is for cm per second. So hence, the rate of increase of water depth is 4 cm per second.